So we've got our tangent line. It touches the circle in exactly one point. And we have the point of tangency, which is the point where the tangent line touches the circle. Okay? There's two theorems that deal with tangent lines. Okay, the first one says if a line is tangent to a circle, then that tangent line is perpendicular to a radius of the circle drawn to the point of tangency. Okay. So let's draw another circle. And let's draw another tangent line. So tangent line can be anywhere on our circle. I'll just draw one up here. So there's my tangent line. Now this theorem says that if we've got a tangent line, then if we draw a radius, so a line from a segment from the center to that point of tangency, we will get a right angle. They are perpendicular. I notice that would apply if I came back up here and I drew the same thing, right? That's still a right angle. It doesn't matter where the point, the tangent line is. Okay, that's the first theorem. The second theorem is if two line segments are drawn tangent to a circle from the same exterior point, they are congruent. So go ahead and draw a circle. And let's draw a point outside that circle. I'll draw one over here. I'm going to call that point A. Now, if I draw a line that is tangent to this circle, starting at point A, and now notice there's only one possibility. There's only one line that does this. All right, there would be that line. There's the point of tangency. If I draw another line starting at A that's tangent to the circle, oops, make that a little bit lower. Down here, that's tangent. Okay, kind of messed that one up.
On this side of it?
Yeah, it should be tangent, right? If I call this point B and this point C, this theorem says that those must be congruent, those segments. So in other words, AB, segment AB is congruent to segment AC, which means that the length of AB is equal to the length of AC. Now, in any kind of pulley system, this is kind of important because think about it, if this were a pulley and I had another pulley over here, I've got this exposed belt. This theorem basically says that the part of the belt that's exposed will be the same length no matter where I move my pulley. The top and bottom will be the same. And so if I'm planning for a pulley system or something like that, that might come in as useful information for someone. That's not the only place where this is useful. But this also can be used to find your a satellite or a spatial's altitude. Because if they're high enough in space, they can see both sides of the Earth, basically, this big sphere, right? So they can have these stations and get this tangent line, right? And they can actually find, if we know these are the same, we can use that information to find the distance to the Earth. So we can actually calculate our altitude. We'll do an example of that here in a second. Okay, so first example, first theorem. Okay, we've got segment AT is tangent to circle C at point T, and it says find X. Now, first off, notice X isn't AC. X is just this little part outside the circle from A to that point that's on the circle. Okay, so our goal is to figure out that length. Now, the first theorem says if a line is tangent to a circle, then it must be perpendicular to the radius. So notice AT is tangent to the circle, and CT is the radius. So those must be perpendicular. Well, now what shape is CAT? It's a right triangle. So we can use the Pythagorean theorem to find AC, right? Now, which is not what we're looking for, but we can find it. So let's go ahead and find AC. So let's see, Pythagorean theorem. AC is the hypotenuse, right? It's the longest side across from the right angle. So square root of 11 squared plus 8 squared. So we're looking for the hypotenuse. A squared plus B squared equals C squared. And so we get 13.6015 or something, 0.02. So that's AC. Now that's not what we're looking for, right? We're looking for X. But if we know AC, if we could just figure out how long this part is, then we could cut it out, right? We've left this. So do we know how long that is? 8. Why is it 8? So that's the radius. So that must be the same as all radii, right? They're all the same. So that's 8. So that means that X would have to be 13.602 minus 8. So it must be 5.602 inches. It's the length of that segment from A to curve of X. Example 2 says AD and BD are both tangent to circle C, respectively at points A and B. Find the value of C. So notice D is exterior, right? Just like A was exterior here. But this time we have two tangent lines. And the second theorem up here says if you have two segments that are drawn tangent to a circle from the same exterior point, then they're congruent. So that tells us that these must be congruent. Which means that 2z plus 6 must equal 46. And that's an equation we can solve. We can subtract 6 from both sides. So if 2z equals 40, then z must be 40 divided by 2. Which is 20. So these are the two primary theorems we're going to use for the tangent lines. A couple of additions to some vocabulary. So we've talked about inscribed before. We haven't really talked about circumscribed, but that's the reverse of inscribing. So when a polygon is circumscribed about a circle, the polygon is drawn outside of the circle such that each of the sides of the polygon is tangent to the circle. So I'm going to draw a circle. Okay. If I circumscribe a square about this circle, then I would draw a square outside of the circle where all four sides are tangent to the circle. So that would be a square that's circumscribed about that circle. Okay? Now, this is the exact same thing as inscribing a circle inside of the square. Okay, so what if we start off with a square and I inscribe a circle? Well, that would be the same thing. I'm going to have all of the sides are going to be tangent to the circle. So from an observer's perspective, all they see is the final product. There's no difference. They're the exact same thing. We have a circle inside of a square. The difference between circumscribe and inscribing is what came first. You're circumscribing about a circle. That means the circle was there first, then you drew the square, or whatever the figure was. If you're inscribing, that means the figure was there first, and we inscribed a circle. Okay. But you get the exact same outcome.
Yeah.
So that's only so that whenever you see the circumscribed about a circle, you say, okay, well that means the circle was here first, we drew the triangle around it. If it had said the circle was inscribed in the triangle, that means the triangle was there first, and then we drew the circle. What's that? No, that's the point. It's the same thing. Okay, but it would make a difference if it said like a square is inscribed in a circle. Then you would have the circle first, and you'd be drawing a square inside of it, right? So that tells you, it's telling you kind of what's inside of what. Okay, so this says a triangle ABD is circumscribed about circle C. So that means this circle's in the middle. We got this triangle going around it. Okay, the perimeter is 27. Find X. Now again, notice X is not dB. It's this distance from D to this point of tangency. All right? So that's what X is. Well, the second theorem that we looked at had, if we have an exterior point that had two tangent lines on the circle, then those segments must be congruent. So that means from B to this tangent line will be the same as B to this tangent line. So this must be congruent to that. And from A to that tangent line, well, that must be the same as A to this tangent line. Or point of tangency. I'm saying tangent line, I mean point of tangency. So A to this point of tangency is equal to A to this point of tangency. And finally, D to this point of tangency must be the same as D to this point of tangency. So that's congruent to that. So if from B to this point of tangency is 3.5, how long is it from B to this point of tangency? Okay, so they're congruent, so it must be 3.5. Likewise, A to this point is 4.5, so A to this point must be 4.5. And then, so what is D to this bottom point of tangency? X is the same as this X. Okay. Well, now we're told the perimeter is 27. how do we get the perimeter of a figure, a polygon? Out all the sides. So this left side, AB, well, that's 4.5 plus 3.5. And then BD, well, that's 3.5 plus x. And then DA, well, that's x plus 4.5. So combining like terms, we've got 2 x's. And then 4.5 and 3.5, Justin said, was 8, right? So 450 and 350 is 8. And those are 8, so that must be 16. So 2x plus 16. And that's our perimeter, which we know is 27. So 2x plus 16 must equal 27. And that's an equation we can solve. It's a two-step equation. So subtract 16 from both sides. So 2x must equal 11. Cut each one in half. So x must be 5.5. So we use the second theorem there. Right? If segment PQ and segment PR are tangent to circle C, the radius is 7 feet, respectively at points Q and R, and QP equals 20, find PS. Now there's this word respectively. This is the second problem that's had that. Remember, we talked about this last semester. Respectively just means in the order that's presented. So PQ, PR, right? Respectively, so that means Q, it's tangent at Q, right? Segment PQ is tangent at Q, and segment PR is tangent at R. So that's all the respectively is telling us, is it's in this particular order. Which if you look at PQ, that makes sense, right? PQ, tangent at Q, PR is tangent at R. All right. So let's start by labeling kind of what we know. All right. So we're told QP is 20. So go ahead and find QP, and let's label that 20. Okay, what else do we know? Do we know, say it again? How do we know that? So they're congruent, right? They're congruent. And because of that second theorem, right? They have this, they both start at P and they're both tangent to the circle, so they must be congruent. That's that second theorem we saw there. And then we said the radius. So what's one of the radii? Okay, so CR is 7. Anything else? QC is 7. And SC is 7. And it's saying find PS. Well, that would be this guy right here, right? PS.
So, I know.
So this is that example I was talking about, where as an astronaut on the space station, I can basically look out my window and I can see Earth, right? And I can get these tangent lines. And if there's some station over here that I can get these distances, which many times there's satellites, and I can get this tangent line, then I can actually calculate my distance to the planet Earth, like the actual physical distance. So let's see here. What do you think?
From P all the way to C, that's pretty much kind of the same as P to R and P to Q, right?
Okay, so that's a good question. Is PC the same as PR?
No.
Is it more than or less than that? Why? Okay, so it goes into the circle. Okay, that's pretty reasonable. That's actually into the circle. So do either of our, so we've already used the second theorem to get these. Does the first theorem apply here at all? Do we have any points of tangency and a radius so that we know it's perpendicular?
We have right.
Sure. CR is a radius and PR is a point of tangency, so this must be a right angle. And so PCR, that's a right triangle. So we can use the Pythagorean theorem to figure out PC. So we can answer that question. Is it 20? All right, so PC, well, PC is the hypotenuse of that right triangle, so we're going to add. So square root of 20 squared plus 7 squared.
So then it's 20 times 20, that's...
Well, yeah, we're taking square root. It's 400.
It's 400, and then that's 40.
So we put that in the calculator.
449.
But it's the square root of 449. And we get 21 point what?
1896.
So 1896, so 190. Okay. So it's close to 20, but it's a little bit longer, right? And we're talking about thousands of kilometers or something like this over the planet Earth, well, that's the big difference between 20 and 21,
I was
right?
almost right.
Okay. So let's see here.
-7 because of radius.
Okay, so if we have PC, that's the whole thing, right? And we're only looking for PS. So PS would be PC minus, cut out that radius, that SC, right? And so 21.1896 minus 7 would give us 14.1896. In this case, it's feet. So the general idea here is, using these two theorems, we can find a whole lot more about the circle than is initially given to us. Okay, and about the tangent lines and everything like that. We can actually find a lot of these distances, even though they're not explicitly given. We can calculate them using either the Pythagorean theorem or the fact that the segments are congruent. So as you're starting to work on the assignment, there's 8 problems. They're not super long, but you should look for all you're using these two theorems, or these two theorems. And so you should look for opportunities to mark angles right angles and mark segments congruent. The other trick is finding the radius in various places, right? So if you know the radius of the circle, it's the radius everywhere. So for example, on number 1, we're told that this is 7, but that also means that CB is 7. So I may start off by marking that 7. I know it's true, right? We're also told AC is 19. So I say, well, AC is 19. All right.
So then
Nothing else is given. So then I go back to my theorems and I say, well,
So doesn't that make AB 19?
no, it doesn't. So, but AB is tangent and CB is a radius, so that's a right angle. Okay.
Oh, yeah.
Notice our second theorem only applies for 2 tangent lines, right? Not one tangent and one going to the center. Gotta be careful there. So now we can use the Pythagorean theorem to figure out x. Okay.